single day are like, well,
So the,
you know,
the
if you died in the lab,
there is
at least you wouldn't have to go through this administration.
Does anybody have any questions before we start? I have one comment about the lab. Apparently we had some problems measuring the DC gain of an operational amplifier. I was not aware that we were going to get hung up on that yesterday, and so I apologize for not getting that straightened out. I hope you go back and try to finish that up. Hopefully Ben and Pallavi will be around to help you next week to make that happen. But I did observe a couple of things going on that concerned me a bit in regard to your use of the test equipment. Oscilloscopes are very useful, and every waveform that you look at, you should be monitoring it on an oscilloscope. Triggers on oscilloscopes are important because they can make the waveform sit still instead of run across the screen. And I saw some issues with people not taking advantage of the triggers on the scopes. So hopefully when you go back and repeat this measurement, if you're not already doing it, you'll also come up to speed again on doing a trigger on the scope. Okay. I'd like to talk some more today about single stage amplifier design. I'll talk about common mode operation. I'll talk about the design of a basic differential amplifier. I'll start talking about slew rate. And then I'm going to define something called a reference amplifier. In 330, we had a reference logic circuit, reference inverter. And we tried to look at how characteristics of different circuits compared to that of the reference inverter. We're going to try to create a reference op-amp here too. It's going to be a simple op-amp, one of the first ones we build. It makes sense to go to a more complicated op-amp only if there are properties that are better than those of the reference inverter. So we'll start out with the reference op-amp. So we'll come out with a reference op-amp as well. So here's where we're at. We're still talking about single stage low gain amplifiers. Although I haven't defined what low gain is, low gain amplifiers are ones that probably have a voltage gain in the neighborhood of 40 dBs or something. When we get to high gain amplifiers, we're going to be approaching 80 dBs or maybe 100 dBs of gain. Last time we talked about common mode and difference mode analysis. And let's see, what do we do here? We talked about going from a quarter circuit to a fully differential amplifier. And we saw that if the conductances were the same, the output conductances were the same, that we had a factor of 4 reduction in gain from what we had with the current source biasing of the quarter circuit. Okay. Let's see, what did we do here? Differential gain. We saw if we had a differential output instead of a single-ended output, the gain went up a factor of 2. The gain bandwidth product improved as well. And then at the end of the period last time, we talked about a way to use superposition to analyze circuits. Instead of using the inputs V1 and V2 to a circuit, we talked about using differential inputs and common mode inputs. I guess we had a theorem. The differential output of any linear network can be expressed equivalently as A1V1 plus A2V2, where A1 and A2 are the gains from the 2 inputs to the output, or equivalently as A common V common plus A difference V difference. And if we want to apply superposition, we can apply superposition to either V1 and V2 or to V common and A common. And then we had a theorem that says the symmetric differential output voltage, there's a mouthful here, the symmetric differential output voltage for any symmetric linear network excited at symmetric nodes can be expressed as V out is equal to AdVd. There is no A common, V common here. There's only a difference mode gain present. If you don't want a common mode gain present, and the common mode gain affects something we'll talk about later called the common mode rejection ratio. This tells you what architectures will inherently have no common mode gain. So today I'd like to talk about common mode operation, design of basic amplifiers, and so forth. So here's how we do common mode and difference mode excitation. If you have any linear network, if you want to find the difference mode gain, you put VD over 2 and minus VD over 2 in, and look at the output, and calculate the output as a function of VD, and that will give you the difference mode gain. And then you can put the common mode input into the two inputs. Again, that's one voltage source, and calculate the V out over V common, and that gives you the common mode gain. Now, this might look like there's two inputs, but there's really not two inputs. You can look at it this way. You can look at a circuit that's got VD here, and you can think of that going through an E source. So it has one output of VD over 2 and another output of minus VD over 2. You can use the basic E sources to do that. So there's really only one input to your system, and that's VD, not VD over 2 and minus VD over 2, right? Common mode gain. We'll look at single-ended outputs and a tail current bias. We'll look at differential outputs and a tail current bias. We'll look at single-ended outputs and a tail voltage bias. We'll look at differential outputs and a tail voltage bias. So there's 4 different common mode gains that we can get now from this basic amplifier structure. So let me consider the tail current bias amplifier with common mode inputs. And if the network is symmetric, I can break this tail current bias into 2 biases, each of value I bias over 2. And if I look at this resulting network, it's still symmetric along this axis of symmetry. If it's symmetric along the axis of symmetry, it's completely symmetric, I know that I symmetric is equal to 0. And if I symmetric is equal to 0, then I can consider half of the network, and this is called the common mode half circuit, right here. And notice this has the common mode output here, which is the same on both sides, and it has the common mode input. Okay, so this is a common mode half circuit. If I want to analyze that common mode half circuit, I can sum currents at this node by Kirchhoff's current law, and I get this equation. I can sum currents at this node, and I get this equation. And I can observe that VC is equal to V1 plus Vx. So this gives me 3 equations. And I have unknowns in this, V out, which I want, V1, which I don't want, Vx, which I don't want. So I can eliminate Vx and V common from these 3 equations, get one equation that relates V out common to V common. And if I solve these 3 equations, I find that V out common is equal to 0. So I find that the common mode voltage gain for this circuit is 0. Okay. Notice I've assumed an ideal tail current source. If the tail current source was not ideal, then I would have to replace the tail current source by a small signal equivalent. The small signal equivalent I have for this right now, if it's ideal, is what?
Open circuit.
Open circuit. If that current source were not ideal, I would have a resistor in there. And then if it's even a halfway decent current source, that resistor would be very big. If there was a resistor in here, I would have to add one more element on this node here. If I added an element to this node here, I would not quite find AC equals 0. I would find that there's a small common mode gain. But the common mode gain would be very small. Yes?
So our aim always to make common mode gain 0 is because of noise or something?
No. I didn't say that was our goal.
Okay.
If our goal is to build an operational amplifier where the output is equal to some constant times the differential input, then we want the common mode gain to be 0. But we could have applications where we don't necessarily want the common mode gain of the amplifier to be 0. Usually we do. Usually we're building differential input amplifiers where we want the common mode gain to be 0, but it doesn't have to be. Now I'm going to put a tail voltage bias in. How did the small signal common mode gains vary if we have a tail current bias or a tail voltage bias? Do you remember that? They what? They were the same. Why were they the same? Not just because of symmetry. There was another reason they were the same. For any symmetric circuit, what about all the voltage on the axis of symmetry? They're 0. So we had the same half circuits that we use to analyze the difference mode gain, right? So the difference mode gain, whether we have a tail voltage bias or a tail current bias, are the same. We now know that the common mode gain is 0 if we have a tail current bias in this idea. Now we're putting a tail voltage bias in. Put a tail voltage bias in, I can put 2 voltages VSS here. Again, there's no current that flows here, so I can drop this off and I look at a half circuit. And this is my half circuit. Is this the same half circuit I had before? Is this the same half circuit I had for the tail current bias? The answer is no. Small signal equivalent of VSS is a short circuit. Small signal equivalent of that node before was an open circuit. So we're going to get a different small signal equivalent circuit. So now we've grounded this node instead of floated this node. Okay. Kirchhoff's current law of this node is the same as it was before. And now V1 is equal to V common since I've grounded this node. And I can solve for V out. I can eliminate V1. There's one extra unknown in here. And that extra unknown is V1. So I can eliminate V1 from these 2 equations. And I get V out common over VC, which by definition is the common mode voltage gain, is equal to minus GM1 over SC plus G1 plus G2. This circuit has a rather large common mode gain. The DC common mode gain is GM1 over G1 plus G2. This common mode gain is comparable in magnitude to the difference mode gain. Okay. So this circuit will not reject common mode signals. This isn't a very good differential amplifier. Does that mean we're going to throw it away? No, we like to have a lot of toys in our toy box, right? Well, it's important that the common mode gain be small if you're going to be putting in signals that have a common mode component present that's significant, and you don't want it to affect the output. We're going to find that oftentimes we will build circuits so that the output of one stage has no common mode signal. If you have built a circuit that has no common mode signal, do you need to have a differential amplifier that rejects common mode signals? No. So we're not going to throw this away. But if you're concerned about common mode signals, it might only be useful if there's no common mode signal at the input. When we get to two-stage amplifiers, we may start with the first stage with the tail current bias. If there's a tail current bias on the first stage, the common mode gain is 0. So common mode signals will be rejected at the output of the first stage. If we go into the second stage, since there's no common mode signals, they could easily go into a tail voltage bias on the second stage. Does that make sense? Okay. Overall transfer characteristics, just add them together. Last lecture, we calculated the common mode gain, the difference mode gains. Today, we calculated the common mode gains. I want to go back briefly with this analysis I did. I've made the statement that the approach I'm following is somewhat different than most authors follow. It's different in the sense that I start with a quarter circuit and I synthesize the whole amplifier from that. But most authors recognize a half circuit. So this analysis we did with the symmetric half circuits, that's been around for a long time. Does that make sense? Let's talk about the design now of the basic differential op amp. Recall, if we start with the common source amplifier, the single transistor common source amplifier, we get this differential amplifier shown on the right. And we calculated last time the gain bandwidth product and the bandwidth. I don't have it written down here. And we did these almost by inspection, right? We did these almost by inspection from the properties of the quarter circuit. In the small signal parameter domain, the parameters, the gain, and the gain bandwidth product are characterized by the small signal parameters GM1, Gout1, and Gout3. If you look at the natural parameters for this amplifier, if you know, since we assume symmetry, if you know the dimensions of M3, you know the dimensions of M1, you know the dimensions of M5, and you know the two bias voltages VB1 and VB2, their circuit's completely specified. So the natural design parameters for this circuit are the 3 W over L ratios and the two bias voltages. There are 5 design parameters. This current better split equally and form these two currents. And the sum of these two currents needs to be this current. So that's a constraint due to the architecture. So in the natural parameter domain, we have 5 design variables and 1 constraint. That means the net degrees of freedom is 4 in this design. Yes?
I was just trying to remember our expressions for our gain bandwidth product and our open loop gain. They're only dependent on the parameters from M1 and M3, and is that just because the circuit is symmetric, so
Yeah.
parameters for M2 and M4
Yeah.
are the same?
Right, we're assuming symmetric, so
Okay.
I could have called this Gout1 or Gout2.
Okay, cool.
This could be Gout2 or Gout4.
Okay.
Yeah, thank you. Expressions for, if we're going to use this to design, and if A0 and GB are 2 important parameters, expressions for A0 and GB in terms of these natural parameters are really tedious. That was true for the quarter circuit. When we looked at the quarter circuit initially, and we looked at the natural parameters for that, we saw the expressions for the gain and the gain bandwidth product for that quarter circuit were really nasty in terms of the natural design parameters. Things don't get easier when you put two circuits together. Okay? So the expressions for A naught and GD in terms of natural parameters are messy. I could write them down. I certainly don't have space on the bottom of the slide to write them down. So we can ask the question, can we obtain a set of practical design parameters for designing this amplifier? Well, there's 4 degrees of freedom. So how many design parameters do we need? 4. Recall that when we just looked at that quarter circuit, we used VXS bias and power as our practical design parameters. I'm going to propose that the excess bias of the 3 transistors, M3, M1, and M5, along with the power, form a set of practical design parameters for this single stage amplifier. You may be able to come up with an alternate set. Whatever set you come up with better have how many in it? 4. Okay? So my premise is those are a set of 4 parameters that are very useful for designing this amplifier. So now I'm going to express the performance characteristics in terms of these practical parameters. I really should have done it in terms of natural parameters because I would have these big, ugly expressions here. Okay? Well, if you put in the practical parameters, you can, G out is equal to lambda IDQ, and GM is 2 IDQ or VXS bias of the first transistor, so IDQs cancel, and you can show that the gain is 1 over lambda 1 plus lambda 3 times 1 over VXS bias 1. Can we comment, can we make any observation about this expression?
It's pretty simple.
Pretty simple. And it separates process parameters from architecture parameters. Okay? As we observed for the quarter circuit. And it involves how many of these practical parameters?
1 to 1.
Just 1. Is that attractive?
Yes.
Yeah. In fact, for this circuit, no matter what you do with it, at the end of the day, if you don't know what the gain is, the only thing you have to know, since this is fixed by the process, the only thing you have to know is what? The excess bias 1. If you want to set, again, a certain value, all you have to do is set the excess bias 1 at that value. Do anything you want to the other parameters, they won't affect it. Make sense? Yes?
So again, the only assumption to get that expression is just that we're symmetric, right? That is
Yep.
the only thing that's been made.
That's the only assumption that's been made. Gain bandwidth product. Given by this expression. Again, it's easy to plug in 2 IDQ or VXS bias and replace IDQ by P or VDD, and we get this expression. Again, I've chosen to separate it into, did I do it right here? No, I didn't separate it. I could have. I could have put P over VXS bias here times something else. And then I would have separated it in terms of architecture parameters and model parameters. So what do we know about, once you set the gain, what do I know about the gain bandwidth product?
It's proportional to your power consumption.
Where's the power?
Coming from
Case closed.
VDD.
Case closed. Set the gain, that fixes VX's bias. Once VX's bias is fixed, set the power to get the GB. Okay? Look at our problem. We have 4 design variables. I've only used up 2. Is that a bad problem to have? No, it's a real good problem to have. What does that tell us?
We have lots of freedom.
We what?
We have lots of freedom.
We have more degrees of freedom, and when we use those other two parameters, we don't have to worry about screwing up the GB, or we don't have to worry about screwing up the gain. We've got the gain and the GB fixed. Make sense? I can't emphasize strong enough how you would have a difficult time making those observations if you were in the natural parameter domain. So how you look at the problem can make a big difference into how hard the problem will be to design. You decide to use this architecture. Your boss comes in and says, you can't let Vx's bias be any smaller than this, and I want to gain above a certain level. You look at this equation, you can say, yep, I'll do it, or it's not going to happen. Make sense? So we still have 2 degrees of freedom left to do other things with. So we'll have to decide what other things we want to do with those other degrees of freedom. What? Now, I keep putting this note on here, need a common feedback circuit to establish VB1. That doesn't eat up our degrees of, it's not eating up our degrees of freedom. We just have to do that because this is a really high gain circuit. So we've got to be sure that some of those 2 currents coming out of the top are equal to the current on the bottom. We will come back and address that issue later.
Dr. Geiger,
Yes.
How did we exactly come to that determination that we have 4 degrees of freedom? Is that just by inspection?
That's a good question. Let's go back and look. I look at the structure here. I assume it is symmetry.
Yep.
So the question is, what do I have to do to be ready to do layout? What do I have to do to be able to build a circuit? And I say, if I size this device, I pick this voltage. I size this device, and I size this device, and I pick that voltage, I'm done.
Focus, it's only the half circuit that we're worried about.
No, it's a whole circuit, but since it's symmetric, I can look at the half circuit.
Okay.
So I looked at everything that has to be done in this design to be complete. There's only 5 things I have to pick, and that completely characterizes that structure. So that's where I get the 5 practical design parameters. Make sense?
How do you subtract?
There's one constraint. The constraint is this current has to equal the sum of these 2 currents. So that's a constraint imposed by the circuit. So I start with 5 parameters, and then I have a constraint. So if you have 5 variables and 1 constraint, that leaves 4 degrees of freedom. I could add a couple of constraints now. I could add A0 and GB as constraints. And then instead of having 4 degrees of freedom, I would have 2 degrees of freedom left. If I look at the differential output, we saw that the gain doubled because it was symmetric. And so these are the design equations for the differential output. Still has 4 degrees of freedom. We could again use the same practical parameter domain to design the fully differential circuit. So, question is, which one should be used if we have both a tail current and a tail voltage bias? Now, if you look at the tail voltage bias, we lose 2 of the design variables. We don't need the transistor M5, so we don't need a bias on that, and we don't need sizes on it. The common mode input, so here's characteristics we'll observe. The common mode input range is large for the tail current bias. So if you have the tail current bias here, your inputs can go up and down a lot, and this voltage will be pulled with them up and down a lot, so you have a large common mode input range. So if you're building feedback circuits, that might have an input on the plus terminal. This might be a low gain amplifier. If there's a big voltage on this terminal, that will cause a large combo input. Input will go up a lot, down a lot. Okay. Everybody with me? This voltage and this voltage are about the same. So if this voltage is going up and down, your combo input is going up and down with the input. Combo input range is large for tail current biases. So if you have a large combo input, because the application is going to put a large combo signal on, then you probably want to use a tail current bias. Improved combo rejection ratio for tail current bias. We just analyzed the combo voltage gain with tail voltage bias, and it was pretty high. So if you are concerned about the combo rejection, you want to use the tail current bias. There's 2 extra degrees of freedom for the tail current bias that you have relative to the tail voltage bias. But there's improved output voltage swing for the tail voltage bias. So those are kind of the trade-offs we have here. Let's talk about slew rate. So we looked at different parameters. So far we've looked at parameters related to the small signal operation. Now we look at kind of a little bit of different parameter, and this is slew rate. Definition. The slew rate of an amplifier is the maximum rate of change that can occur at the output node. So if you have a differential input amplifier and you put some input in, you put an input in that's big enough that the amplifier goes nonlinear, then your output will try to respond, and your output can only change so fast. The slope of this is, by definition, the slew rate. We have 2 slew rates. We have a positive going slew rate, and we have a negative going slew rate, depending on whether you put a positive input signal in or a negative input signal in. So the slew rate is a nonlinear large signal characteristic. The input is overdriven. And usually when it goes into slew, during slew, your devices will enter a different mode of operation, and the gain will go down. Your transistors may normally be operating for MOS devices in the saturation region. When it goes into slew, some devices will go into cutoff, and some will go into triode region. Hard input overdrive is what I'm depicting here in the figure. And typically, when it goes into slew, it'll be a straight line. The slew will invariably be a straight line. Slope will be constant. Usually, the magnitude of the slew rate in the positive direction and the negative directions are the same. So you've got a positive slew rate here, a negative slew rate here. We can design circuits so the slopes are different. But most of the op-amp circuits we will look at, they will naturally have the same magnitude of the slope. We'll see why that's the case shortly. So let's look at this amplifier we've been involved with so far. With a step input on VN plus, I'm going to put a step input on this input. If I put a step input on this input, I'm going to try to turn this transistor on hard. And I'm going to take, if this transistor turns on hard, I'm going to try to steer this tail current to the left side. The way this circuit works is when this voltage is higher than this voltage, more current goes to the left. When this voltage is higher than this voltage, more current goes to the right. If I put a big step on the input between VN plus and VN minus, I'll steer all the current to the left. If I steer all the current to the left, this transistor will enter cutoff. If this current is all here, so this is the tail current, this tail current will be coming here. And if this is off, half the tail current should be flowing here. This voltage is fixed, VB1. So half the tail current will be flowing here. And that tail current will be flowing into the load. That half the tail current will be flowing into the load. So if I put a step on the input here, I'm going to get I tail over 2 flowing into that capacitor. Are you with me? I put a step in the input here. The current's going to be flowing in that capacitor. It is going to be I tail over 2. Normally, what is the input current to that capacitor if the signal is small? It's 0. The current flowing here and here is normally the same. When you put big inputs in, then you start increasing the relative size of these in it. But normally, this current are the same. So let's look at the IV relationship for a capacitor. We know for a capacitor, the current is equal to capacitance dV dt. Or dV dt then is equal to the current over the capacitance. Since we're putting a constant current in there, this derivative here will be equal to what? The slew rate? The voltage across the capacitor is output voltage. So dVc dt is the same as dV out dt. So we're putting a constant current in the capacitor, and that current's I tail over 2. So that's the slew rate. So the slew rate is what? I tail over 2 times the load capacitance. And that's the positive going slew rate. What if I put a step in this side?
Just the opposite.
Be careful. Opposite effect will happen, but if I put a step in here, all the current will flow here. I tail over 2 will still be flowing here. So the net current that will flow here will be in this direction now, will be I tail over 2. Because this is I tail over 2, this is I tail. This is I tail over 2, so you're going to have to be taking I tail over 2 out of the capacitor. So you're going to discharge the capacitor, but at the same current rate. So the negative going slew rate will also be given by the same expression. Okay, I made the statement that the positive and negative going slew rates are usually the same. We've seen that in this amplifier. Could I build a circuit where it's not true? Yes. Naturally, they tend to be the same. Yes?
So if I'm in the lab and I'm trying to characterize an op amp and I am only putting, in the lab we would probably want to use a square wave since we want to be able to observe the periodicity on the oscilloscope. If I'm not changing which input I put my square wave on from the inverting input to the non-inverting input, am I not truly capturing the rising and falling slew rates?
Yes. If I understand you correctly, you put a big step, positive going step and negative going step on the inputs. You'll see an output that slews down, saturates, slews up, saturates, slews down, saturates, and so forth.
Yeah.
So you will get both positive and negative going slew rates on one display on the scope. The one edge will be the positive slew rate, the other edge will be the negative slew rate.
But I never put, I kept it on Vn minus the whole time. I never had an input on, I grounded Vn plus.
You can do it either way.
Oh.
You have to be sure that the differential input changes sign. So you can fix one of the terminals and put a positive voltage in the other one, and that will cause it to go to one direction. Put a negative voltage on that same terminal, it will cause it to go the other direction.
But you would only capture either slew rate plus or slew rate minus, right? So if you work at your ground, it would just go up and then settle, right?
It depends on what you do. If you put a square wave in, then you'll get both. If you just put a step in one direction, then you'll get one. But to put the step in that one direction, you'll have to reset it to put it in again. So indirectly, you're still putting in a square wave, right?
Yeah.
You just may not be looking at the other edge. Now, if this is a slew rate, this is not in terms of the parameters that we typically have in our design space, in our practical design space. I tail appeared here again. I tail was not one of our practical design parameters. But ITAL times VDD is P. So I can rewrite this like this. Ah, now what do I see? I see that I've got a simple expression now for the slew rate in terms of the practical design parameters as well. But I got a little bit of a problem. If I want to specify 3 characteristics, the gain, the gain mammoth product, and the slew rate, because I've got 2 degrees of freedom left, can I do that?
No, because slew rate and gain bandwidth are controlled by the same.
Slew rate and gain bandwidth product are controlled by the same parameter P. So if I, for this architecture, not all architecture, but for this architecture, if I set the GB at a certain value with P, I'm stuck with the slew rate. If I set the slew rate at a certain value with P, I'm stuck with the gain bandwidth product. So then I might decide which is most critical. And I'll pick P to determine which is most critical. But you got to be careful there too. Because we might be under the assumption that more GB is good. So you might say, well, I've got to meet a slew rate and a GB requirement. And the slew rate is more stringent, so I put the power in to make the slew rate requirement. And then the GB just went up a factor of 10. Yay, right? Is that good? Not necessarily. You won't kill your gain, because the gain was only V excess bias. But if your bandwidth goes up, your integrated noise will go up. So your signal noise ratio may deteriorate. So it's not always advantageous to make more GB than you need. Make sense? Let's talk about the reference amplifier. So this amplifier we've been spending the last 2 lectures on is what we're going to call the reference amplifier. It's an amplifier that has a single-ended output. I light grade this. It's got a single-ended output and a tail current bias. Okay. Here's the gain of the reference amplifier, and here's the parameters that we derived for the gain bandwidth product and slew rate. Now these are really mixed parameters now. They're in terms of small signal parameters, GM1, GOut1, GOut3, and IT. So that's a mixed parameter set. But we can put all 3 of those expressions in terms of the practical parameters. This is probably the simplest differential input op amp. And if its specs meet your requirements, you probably don't need to go any farther. We'll go into more complicated structures then, only if superior performance in some aspect is required. So now let me try to summarize where we're at. We started out with a single-ended, single output structure. In the small signal parameter domain, that common source amplifier with an ideal current source bias had gain GM over Gout and GB is GM over CL. In the practical parameter domain, we had the gain and the gain bandwidth product. Now we have the reference op amp. We have the gain bandwidth product, and the slew rate in the mixed parameter domain. And finally, we have these expressions in the practical parameter domain. Let's ask the question, what basic type of amplifier is this reference op amp? We saw at the beginning of the course that an op amp was any structure that had a high gain, right? But we said some of them are really current or voltage or transistor or transconductance. Which type is this really?
Well, this one has a high input impedance.
It has a high input impedance and
a lowish output impedance.
no, actually a high output impedance.
Oh,
So the voltage.
so then it's a
Transconductance amplifier. This is inherently a transconductance amplifier. Does it really matter?
Well, how did you decide that?
What?
How did you decide that was transconductance?
Let's go back. If you look at the output impedance, we didn't calculate the output impedance, but the output impedance is the impedance you see looking here, in parallel to the impedance you see looking here. This impedance is G out 4, this impedance here is G out 2. And the output conductances are typically small, or the output impedance are high. In fact, this was our way we we used this counterpart circuit to implement a current source, right? So it's as good of a current source as we have with that single transistor or with that counterpart circuit. And this impedance is the same looking this way. So this has a high output impedance and a high input impedance. So does it really matter? Well, many applications it doesn't, and a lot of times we use just this transconductance amplifier. If we want a low output impedance, we can put an output stage on this structure. We'll talk about how to do that later. That's all for today. Thanks.
So it wouldn't, you asked the question, does it